Tuition Uncovered, investing for your future.
The following series of lectures are going to cover acids, bases, as well as buffers. To begin with, I'm going to do just the definitions and explanations of acids and bases, keeping in mind we're going to differentiate between alkalis and bases as well. Moving on to ionic equations and reactions of some of those common acids and bases, how to balance them, how to look at ionic equations, and how to ascertain them by using various examples. Of course, acid-base conjugation is where I'll end before I move on to the next part of the series. This is stuff you should be familiar with from your AS revision, but nevertheless, hopefully a very quick recap. So when we're looking at acids, you're familiar with the idea that acid turns a litmus paper red. That's from GCSE and pre-GCSE days. It turns pH less than 7. Again, something I hope you've learned in GCSE. We can remind ourselves acids are proton donors. This is more the AS stuff for some of you. Protons are H plus ions, i.e. if you have a hydrogen atom, a proton in the middle, an electron whizzing around on the outside in that first shell, take away that electron, which I've shown here in blue, you're left with just a H plus ion, which is effectively simply a proton, because that electron on the outside has been removed. Donate protons, H plus ions, to a solution. That's what an acid is, i.e. these Bronsted-Lowry acids. Examples, we had a look at a general formula. I've got a HA representing a H plus joined onto an A minus, the anion. Doesn't matter what it is for now. The HA in an aqueous, in a water solution, becomes H plus ions and A minus ions floating around. This acid has given H plus ions to that solution. For instance, hydrochloric acid, HCl, splits into H plus and Cl minus. Sulfuric acid here, you see two hydrogen ions from sulfuric acid, so it's diprotic. HCl was monoprotic, gives up one proton. Sulfuric acid is diprotic, it gives up two protons. Of course, SO4 2 minus is the anion, which is going to balance and hold on to those H pluses in sulfuric acid. Nitric acid again is monoprotic, one H plus coming from it, and of course the NO3 minus, the nitrate ion. Now a base, or a soluble base which is called an alkali, are things that turn litmus paper blue. They have a pH greater than 7, and of course instead of being donators of protons like acids, these bases, or alkali, accept protons, these H plus ions, from a solution. So for instance, here, NH3 is taking the H plus and becoming NH4 plus. I've shown it in reverse simply to show you, I guess, the opposite of an acid. It's taking H pluses and becoming NH4 plus, the ammonium ion. That's what ammonia does. It's a very weak base. Other things, such as these metal oxides, sodium, lithium oxide, calcium oxide, these can also accept H pluses from a solution, forming water in neutralization reactions. Again, remind you of some of the AS chemistry. These hydroxides give off OH minus ions that take these H pluses and become water. It's a neutralization reaction. We've seen a few examples before. I'll show you a few again before we go on to some of the more deeper parts of the syllabus. And now very quickly to talk about strong and weak acids. A strong acid is something that completely dissociates into its ions. If I put a bunch of HCl's in a solution, the HCl's would split up into H plus and Cl minuses completely. So would the sulfuric acids and the nitric acids. They're considered strong acids. Weak acids, on the other hand, are ones that partially dissociate in the solution. So here's methanoic acid. It would separate into H plus ions and methanoate ions. And here I've illustrated this, the methanoic acid splitting into H pluses and the HCOO minus, the anion. Now what happens is the equilibrium is far to the left. Most of the methanoic acids stay as methanoic acid, joined together. A few of them, and by that I mean a very small portion of them, will ionize and separate into H pluses and methanoate ions. So this partial dissociation is what makes these acids weak. Methanoic acid, ethanoic acid, remind yourself of AS chemistry and how we've named these. Other biological acids that you may come across, here's carbonic acid, which helps regulate the pH, helps buffer the pH of the blood. It's also a way that CO2 is carried in the blood by forming this carbonic acid. We've also got fatty acids, which are long hydrocarbon chains with a carboxyl group attached. DNA and RNA are nucleic acids. They consist of nucleotides. I won't go into too much of the biology at the moment. Here's an example of a amino acid. Here's an example of an amino acid, serine, specifically an alpha carbon in the middle, an amino group which is basic, a carboxyl group which is acidic, the H, and of course then an R group. In this case I put a CH2 and an OH because it's a serine. Now what's happening is these amino acids can have an acidic nature and a basic nature. Because they have both, they can act as an acid and a base. They're referred to as amphoteric. Nevertheless, the key point for this particular part of the lecture, weak acids are ones that partially dissociate, as I've given an example with methanoic acid. Strong acids completely dissociate into their ions. If we look further into this, we see sulfuric acid is diprotic. When it dissociates, it's going to relieve itself of one proton at the particular pH. Eventually, the hydrogen sulfate ion will release the next proton to produce H plus and the sulfate ion. So because it's diprotic, both hydrogen ions are not released at the same time. They're released in steps. Here's a triprotic acid, releases 3 protons per compound. Phosphoric acid, useful to remember, just like sulfuric acid, this will also release 1 proton at one stage, then another proton, and then the third proton at a later stage. So they relieve themselves of protons at stages. Now, this here is a construction of the pH scale. The pH scale runs 7 being neutral, anything less than 7 is acidic, above 7 is alkali. The numbers go even below 0 and can go above 14. Effectively, the pH is a reflection of the hydrogen ion, the proton, concentration. These square brackets mean moles per decimeter cubed, concentration, specifically here the hydrogen ion concentration. Now, the more concentrated the hydrogen ions, the lower pH. The less the concentration of the hydrogen ions, the more the pH. So, for instance, if we look at neutral, 10 to the minus 7, 1 times 10 to the minus 7 moles per decimeter cubed. If we increase the concentration from 10 to the minus 7 to 10 to the minus 6, increase the concentration by a factor of 10, that causes the pH to decrease by 1 unit, i.e. the more the concentrated the acid, the lower the pH. And you can see that as you move along this scale. Likewise, if I had diluted by a factor of 10 and gone from 10 to the minus 7 to 10 to the minus 8, the pH would have increased, it would have become more alkali. So as the amount of hydrogen ions decrease, the pH is going to continually increase. We can also at this point look at OH minus ions, the hydroxide ion concentration. That can give us something called the POH. Now, I won't complicate the story just for yet. Let's stick to some basics. Stick to pH. 10 to the minus 7 moles per decimeter cubed the hydroxide ion concentration. The more the hydroxide ion, so if we're going this way, towards an increased concentration, effectively the solution becomes more alkali, the pH rises. If, however, we decrease the concentration of hydroxide ions, that's going to decrease the pH and make it more acidic. Now, the hydrogen ions and the OH minus ions appear in a balance. As you increase hydrogen ions, you decrease the hydroxide ions and vice versa. So when we look at water, water naturally has a dissociation into H plus and OH minus ions. And here I've shown you this H2O dissociating into H plus ions and OH minus ions. Now, generally, the position of equilibrium is far over to the left. There's very few of these H pluses and OH minus ions. So water with a pH of 7, 10 to the minus 7 is the concentration of H plus, and 10 to the minus 7 is the concentration of OH minus. When we look at Kw in a few moments, this will be even more relevant. For now, just appreciate water has a few H pluses and OH minus ions floating around, very dilute concentrations, but if you were to increase the amount of H pluses, say by adding one of these acids, you would also decrease the concentration of the OH minus ions, and that would decrease the pH as well. I hope that's not confusing you. If you're going to take away anything from this, the greater the H plus ions, the lower the pH, the greater the OH minus ions, the higher the pH. Now, before we end, a quick mention of the hydroxonium ion, which I've shown you here. You've seen the H plus ion concentration. This is effectively also the hydroxonium ion concentration. This here is when H2O meets the H plus, they bond together to become H3O plus, and there is strong evidence that hydrogen ions don't exist simply as protons, which, as you remember earlier, we discussed this, when the electron leaves a hydrogen atom, leaves behind a single proton, which is the hydrogen, the H plus ion, that joins water molecules to become the hydroxonium ion, and that is how H pluses are found. Join onto water to become hydroxonium ions. You may see this in books. This is what it's referring to. I'm not going to go into the evidence just yet, but just so that you know, that's how H pluses generally are found. However, there is no problem representing H plus ions as they are when you're looking at acids and bases in various reactions. So let's move on to the next part of the series. And not forgetting our discussion on acid-base conjugation. So here, again, I'm generalizing with HA being our acid, dissociating into H plus and A minus in an aqueous solution, reminding you that I spoke about HA and H2O. The H plus joins the H2O to become H3O plus, the hydroxonium ion, and of course we have our A minus ion floating around. Here we have HCl as an example. There's covalent bonding here between the two. This and water, the dot cross diagrams both are shown. We can now look at H3O plus as a dot cross diagram with a dative covalent bond between this pair of electrons, a lone pair on oxygen, and the H plus ion. Dative covalent, remind yourself from AS chemistry, where in a covalent bond, the pair of electrons came from one atom. Overall, that has a positive charge, and of course this is our Cl minus. The cross amidst those 7 dots, representing the extra electron, giving it the negative charge. Dot cross diagram should be pretty straightforward. If we now look down here, HA with H2O becoming H3O plus and A minus is a useful example to appreciate acid-base conjugation. First of all, left to right, the HA is the one donating a proton, so it's the acid. On this side, the H2O accepting that proton is the base. On the other side, however, if we go backwards, it's the H3O plus, the hydroxonium ion, which is the acid because it's going to give up a H plus to go this way. The A minus is accepting the H plus, so therefore is acting as a base. We can now pair these up. An acid on the left becomes a base on the right. A base on the left acts as an acid on the right. Keeping in mind we're talking about the reverse. So the acid base pair is there, and a second base and acid pair is there. This is conjugation. You must be able to look at a reaction and decide what the acid-base conjugates are on either side of the reversible or the straight arrow showing reactants and products. I hope that was clear. We'll move on to other videos now. Now this section here, talking about some of the common acid-base, acid-metal, acid-carbonate reactions, and stuff that you should have done in AS. If we remind ourselves of some of these examples, so hydrochloric acid reacting with magnesium hydroxide, we see salt and water, i.e. magnesium chloride and water being formed, and of course here's the balanced equation. Other examples, sulfuric acid and sodium metal giving off bubbles of hydrogen gas, and of course sodium sulfate. The sulfate because it's sulfuric acid, the chloride because of the chloric acid, and here we have the acid metal carbonate, nitric acid and calcium carbonate example I've shown. Calcium nitrate, carbon dioxide and water. Keep in mind, you should remind yourself of how to put together salts. Keep in mind, of course, the negative anions, the charge on the positive ions, and therefore the balancing of the two to give you your ionic salt. Magnesium chloride, magnesium is a 2 plus, Cl's a 1 minus each. Sodium sulfate, the sulfate is a 2 minus, sodium's a 1 plus each. Calcium's a 2 plus, and the nitrate ions are a 1 minus, so therefore 2 of those are required. If ever you forget the charges on these, look back at the acid. If the nitric acid is holding a 1 H plus on the NO3s, the NO3 must be a 1 minus charge. If the sulfuric acid has 2 H pluses, the SO4 must have been a 2 minus. Likewise, HCl, H must be a 1 plus, Cl must be a 1 minus. Keeping in mind also the definition of salt, when the protons, a H plus from an acid, is replaced with the positive ions, which are the metal ions, or an ammonium ion, if we think of the ammonia reaction in a moment, which can ionically bond to anions, forming, of course, the salt. And that anion came from the acid. So I've tried to color code things to make them easier. This middle example I want to look at further. It's a redox reaction when an acid and a metal react. And here we see, remind ourselves, oil rig, oxidation is loss of electrons, reduction is gain of electrons. In redox chemistry, AS, you would have covered this thoroughly. Just a quick reminder, sulfuric acid reacting with metal. The sodium in its natural state, i.e. unbonded to anything else, not bonded, zero oxidation state. The hydrogens are a 1 plus each. They will then become zero oxidation state on the right, so therefore there's been a +1 to 0 reduction in oxidation state. If it's a reduction, it's gained electrons. The sodium was a 0 over here. They're 1 plus ions in the sodium sulfate, so it's a +1 oxidation state. From 0 to +1, there's an increase in oxidation state. Oxidation's occurred. Oxidation is loss of electrons. This acid metal reaction, of course, is a redox reaction. Now those ionic equations, if we come back to some of these examples, and each of those from the first slide I'm showing you again, the HCl and the magnesium hydroxide, we have a neutralization going on with the magnesium chloride salt and the water being produced. If we now think about physically what's happening, HCl in a solution splits into H pluses and Cl minuses. Magnesium hydroxide, ionically bonded, splits into magnesium 2 plus ions. The OHs are 1 minus ions, and there are 2 of those. On this side, the magnesium chloride salt in a solution are still ions floating around, the magnesium ion and the chloride ions. The water is still H2O, that is as it needs to be. Now if we look carefully, hydrogen ions from being just H pluses have now become part of water. They have reacted. Chloride ions were floating around before, they're still floating around. Magnesium ions were floating around before, and they're still floating around. Hydroxide ions were floating around, but now they're part of water. So if we think about all the things that haven't done anything, they're just floating around, the hydrogen ions and the hydroxide ions have reacted. We can leave those where they are and cross the magnesium and the chlorides out. The magnesium and the chlorides on this side can be crossed out again because they're just floating around, nothing's happened to them. But the water is a new product. It's a new substance in the mixture. Therefore, hydrogen ions and OH minuses stay, the water stays. You're left, once you've removed the spectators, an ionic equation. So what we're saying, when you have a reaction and you remove all the things that aren't actually reacting, they're not actually changing into anything else, the spectators, remove them, what you're left with are the reactions and products, which leads to an ionic equation. Another way to put this is anything that hasn't reacted, combined, or removed itself from something, that hasn't changed its state, mustn't have reacted. Aqueous ions here, where am I? These two have remained so. Only these aqueous ions have become a liquid compound here. Likewise, if you follow the same down here, the hydrogen ions are reacting, the sulfate is not, it's still a spectator. The sodium metal has become sodium ions, and as a result, it has reacted. The sulfate, as I said, is spectators, but the H2 is a gas from H plus ions. That's not a spectator. So therefore, if we take off the sulfates, we're left by default with an ionic equation for this reaction. And likewise, if you look down here, I'm sure it's pretty self-explanatory. And finally, not to dwell on this too long because it is just a simple recap, I'm showing you once again those same reactions. Making a salt, acid and base makes a salt, acid and metal oxides are also neutralization reactions that make salts. Acid and ammonia can also make a salt, in this case an ammonium salt. Have a look at these reactions, remind yourself of the science, remind yourself of how to write and balance these equations for your exams. And again here, I've shown you the removal of spectator ions. The first example we've already seen. The next example, this time I'm using sodium oxide. Again, removing spectators gives us an ionic equation here. And down here with the ammonia, also an ionic equation. This should all be self-explanatory. A lot of it's revision from your AS, but nevertheless important for your A2 exams. finally, I'd like you to have a look at this question, read the question, pause the video, write your answers down to these questions, and of course figuring out this little web here. And once you've figured everything out, check with my answers in a few seconds. And so my answers. So here we see, I'm not going to read the entire question out, it's pretty self-explanatory. First of all, if we're looking at part 1, we had to identify substances X, Y, and Z. Now, with respect to X, calcium's reacting in the form of 3 different compounds. It's reacting with HCl, and those calcium compounds, whatever they are forming salt and various other products. Knowing how the reactions are, we can say the first must be a neutralization, say calcium hydroxide. Could have been calcium oxide as well. Both would have given us a salt and water. The second is leading to CO2H2O. It must be a carbonate of calcium. So calcium carbonate with HCl giving us calcium chloride, CO2 and H2O. And finally, it's producing salt and hydrogen gas. This must be the pure metal, calcium solid reacting with HCl to produce calcium chloride and H2 gas. Now in part 2, these reactions needed to be done. Part 3, the common salt was calcium chloride. Part 4, why the compound is referred to as a salt. I've given you an explanation here. And finally, part 5, writing a balanced equation for the reaction of calcium oxide with sulfuric acid. Once you have a look at this, we can then do our basic molar calculations. The maximum volume in centimeters cubed of sulfuric acid that can be neutralized to 1 decimal place, i.e. we know this is how many grams of calcium oxide, this is the concentration of sulfuric acid. Put all your figures together, see if you've got the same answer as I have. Keep in mind I had asked for the answer to be 1 decimal place and in centimeters cubed. Moles is equal to concentration times volume over 1,000. Keep that in mind, and not to forget, of course, mass over mR gives us moles. 2 very useful equations which are useful also for your A2 exams. And finally, do keep in mind there's a large variety of Q&A questions for you to have a look at with the worked examples and the answers, and some further guidance and exam tips in the Q&A video. Good luck.
Tuition Uncovered. Investing for your future.